Hello everyone, welcome to video 3. This will probably be our longest tutorial because I'll be giving a complete breakdown of the tools needed to learn programming as well as what goes on inside the computer after you run your program. This is way easier than you think, but it's very important that we get this concept down, because if we don't get it down, learning other more complex computer theorems or coding techniques might be very, very difficult. So let's go. We are going to be going through this slide, and I'll just give you a gradual breakdown of what we'll do. So the first is the table of content. So through this tutorial, first we'll go through the brief history of C programming language because I haven't spoken about that in the previous videos, and then we'll learn the tools. We'll learn about the tools needed for programming or needed to learn programming. After that, we'll break down each tool, and then we'll go into an in-depth lecture about what goes on inside a computer when you run a program. That will be the most or will I say the longest part of this tutorial. So listen very, very carefully, especially people who plan to study computer engineering in school. So let's look at the history of C programming language. The language was developed by Dennis Ritchie at AT&T Bell Labs in the United States between 1969 and 1973. It's a high-level, structure-oriented programming language used for general-purpose programming. It's sometimes regarded as a middle-level language because it binds the gaps between machine code and high-level language. So you would have heard, some of you might have not heard of the word high-level language, but high-level language is usually used to refer to languages that are represented with, is used to refer to computer codes that can be represented with English words, like words that could be understood by a normal human being, not ones and zeros or any of those terms using assembly. So you have other high-level languages like Java, like C++, like PHP. Many of them. There are many of them out there that use human language terms to represent information and not ones and zeros. So let's go to the next slide. Now, still on the history of C programming, we'll look at what C programming is used for. First, in design of operating systems, such as Linux, Unix, and also it's used to design other programming languages. This is surprising, but yes, there are programming languages that are designed with C, such as PHP. We even have operating systems that are Linux based that are designed with C, or some part of it are designed with C. Then you have also languages like MySQL used to create database. Yes, it's designed in C. So C is also used to develop systems, system application like database systems, language interpreters, compilers, assemblers, operating systems, network drivers, word processors. I'll go through each of them. So database systems are basically systems that manage database, of course. Then language interpreters. Now interpreters are different from compilers. There are certain languages that are interpreted in the sense that they are switched from one mode to another. So when you say bring, it interprets that, and usually interpreters are slower, but compilers convert your code straight from the written high level code straight to machine code, that's ones and zeros. Assemblers basically convert assembly language to machine code. So assemblers are different from compilers in the sense that assemblers are compilers that compile assembly language. So that's basically the difference in the usage of those terms. Then operating systems, will learn more about what they do in future slides. Then drivers, have you ever wondered how your computer is able to detect your mouse, your wireless mouse, your your keyboard, your game pads, your webcams is drivers. Drivers do those things, so you need to be aware of this. So one problem with C is that it's not object oriented. Object oriented programming languages are popular. So by object oriented, they mean that um, it's different from C in the sense that C you can only work with functions, but object oriented programs you work with classes as compared to C where you just work with functions and structures. You work with classes a lot in object oriented programming languages, and most of the things that they do there is with classes. You can go and read more about this and learn the difference between object oriented programming languages and structure oriented programming languages. So at this point, let's take a break, and I'll see you in about a few seconds. Alright guys, welcome back. So now we'll go straight to the tools needed to learn programming. First, you need a computer which processes the data. You need an operating system. Of course, operating systems are different, are separate um, components in the sense that you need to get an operating system and install it on your computer before you can actually even use the computer. Then you need a compiler, because languages need to be interpreted to a form that the computer can understand. So compilers do that, and normally they come with integrated development environments, which you see in our next tutorials, because that's just the easiest way for beginners um, as compared to professional programmers, who can code directly from the command prompt. Now, integrated development environment, yes, we just spoke about that. It's used to write your code and make it easier for you to do things with code. And then you need some input and output devices. So basically, input and output devices are like your keyboard, your mouse, your smart pen, all that stuff. Then output, those are just input devices that I just listed now. Then output is like your monitor, or your what else could I say as output device? Monitor is the best example of an output device, because it's very familiar. It's something that displays the result of whatever you have done. So just that's the best example I can give. So let's go to the first, which is computers. Now, in order to learn programming, you need a computer. Now, by computer, that word, a lot of people don't seem to understand what the term computer means, but we have computers all over us. Today, they are so tiny, we even don't know that we have them around us, like our smartphones are computers. A Raspberry Pi, as you can see here, is a computer. You even have many other boards that are just like a Raspberry Pi, that are also computers as well. Your desktop, which is the older version that we are used to, are computers as well. Then you have your laptop, which most students today in the university use. That's what I'll use to basically make most of my videos. So just so it's very, very convenient, to move around with and to learn, anything that you want with. So let's go to operating systems. Now, the three most popular operating systems you come across are Windows, Linux, and Android. Windows and Linux you mostly see on PCs, like laptops, and then Android you are mostly used for phones. You even have Android OS, and then you have iOS, that's iPhone OS. Even the Apple also has its own operating system called iPhone OS. So I didn't list that here, but that's also an operating system. So what do operating systems do basically? So operating systems, they basically support a computer's basic functions, such as task scheduling, executing applications, controlling the peripherals like the mouse and input and output devices. Uh, yeah, that's what the operating system does. It's like computers work based on abstraction. there are levels, and each of those levels have their job. So you have the hardware, then in the hardware you have an operating system, which is another level right below it. So it's doing the job of managing. When you press G on your keyboard, the operating system knows that you press G, and it, you know, does what G is supposed to do. You get the idea. So now let's look at Windows in particular, and Linux, which are very popular. Most of us use Windows, but we don't even know that there are other operating systems like Linux. Linux is another popular operating system. People like myself who are in the computer engineering program, we make use of Linux a lot because it's very fast. It helps. Linux helps helps people like us compile very how do I put it? Helps us compile very complex code that sometimes you can't really run on Windows. I'm trying to reposition this so that you guys can read this slide. Let me see if I can reposition this. Alright, let me reposition this right here so it doesn't block. Yeah, so I was trying to get you to be able to read the slides without any distraction. So we have Windows. Windows current version is Windows 10. We all know Windows 10. It's very unique and different from Windows 7. Now, one unique feature of Windows is that it's not free. It's paid, of course, but the payment is so that they can present you the best service possible. They can make your life a lot easier, because when working with Linux is free. Linux is fast, but you need to be really need to be into computers to make use of Linux comfortably, because there are times when you need help. Your certain softwares are so difficult to install. In Windows, you could just click, 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 and the software is installed. But Linux is different. You have to run commands, on your computer, and it could be very, very frustrating sometimes. So yeah, and the advantages of Linux include that it's faster, it's free, it's secure, and then another thing is that you can compile C directly on Linux. Linux, as compared to Windows, where you need to install the compiler or download an IDE, an integrated development environment that comes with a compiler. Linux usually is developed with C and C++, so it already has the compilers there, so you don't even need to install it to learn C. Basically, you just write the code and call it from the command prompt, and that's it. Then another thing about Linux, if you look at this image right here, right below this Windows image, you see like many names here. You have Fedora, you have Raspbian, you have Red Hat, you have CentOS OS, you have Linux has many distributions. Ubuntu, which is another popular one. Some of us might have heard about Ubuntu. It's also a Linux distribution that it's one of the best Linux distributions out there, in the sense that even though it's free, it has a very good development community, and they try their best to update it every now and then. So let me see if there's any other thing that I'm missing. Yeah, permissions. When it comes to Linux, you can basically set yourself as the admin. But for Windows, different versions come with admin privileges. You could have home. Maybe home might not give you that privilege. Pro might give you. Then you have the enterprise. It's like sometimes Windows kind of limits what you can do as compared to Linux. When you become very good at using Linux, man, you could just do anything. Basically, that's what I'll say. Like, it gives you a lot of freedom because it's open source. So I think you have learned the idea behind operating systems. They are just basically that abstraction level right below your hardware that manages all your applications. Your video players, your Microsoft Word softwares, they are all installed like on the operating system. So it manages how they behave, how they execute, and all of that. So let's look at compilers and interpreters, which is breakdown. So when you write the code, let's look at this. This is a C code, for example. Hash include stdio. This. I mean, in the next few videos, you know what this code means. we'll probably run a code like this in our next tutorial. So compilers basically convert this code that looks like English. Main is an English word, print English word. It looks like English even though it's not English. It compiles it into this zeros and ones that the computer will understand, because your computers basically work on two values, zeros, ones, and it manipulates those values to do everything that you're seeing on this screen right now, including my image and all these things. I mean, that's just fascinating, but that's basically what goes on in your computer. It's a manipulation of two values, ones and zeros. Does everything that we can see right here. Now there are many kinds of compilers. Every language has their own compiler. C has its compiler, C++ has its compiler, Java has its own called Java C. C has GCC, Intel C++ is another C++ compiler. ECJ is another Java compiler that is Eclipse compiler for Java. C Python is a Python interpreter, because Python is, some people say it's an interpreted, some people say it's both an interpreted and a compiled language, but Python uses interpreters too. So this is just one of it. Then you have PyPy, PyPy, which is also another interpreter, and many more. So you get the idea. Compilers convert the code that you have written that makes sense, that looks like English, into a machine code. Now imagine you have to write all these ones and zeros. This is just a tiny fraction of what you write, but imagine you have to write millions of these in order just to get this thing done. I mean, isn't that crazy? So it's better to just write this instruction and your computer converts it to all this, because if you have to write these ones and zeros, you're just basically going to go crazy at some point. Many people in the past who developed this language could not bear the pain of having to do this, and I'm very sure that you won't want to, because after you learn how this works, then you know how difficult this will be. So now let's look at integrated development environment. This is basically, I'm sure you'd have seen something like this, where you write the code, it has the folders listed here, it has a bunch of messages or log files or error statements here. You might have seen something like this before. So this is what an IDE looks like. It makes developing your code easier. You can run your code from here, you can write your code here. You can even, it gives you messages on the errors that might have happened and how you can correct those errors. So that's basically a brief description of what integrated development environment, also popularly known as IDEs, what they do. They just make your life easy. Take this right here. All right, so compilers and interpreters breakdown. So let's look at compilers versus interpreters again. So let me look here. Okay, I briefly forgot what I wrote here, but the idea here is basically I came up with a good example of what compilers do. So imagine you went to a different country. Let's say you went to France and you don't speak French. Everybody there speaks French. So how do you tell someone, that my name is Leo, je m'appelle Leo, my name is Leo, but then if you can't speak French and you tell someone my name is Leo, they won't understand you. This is the same thing with a computer. A computer only understands ones and zeros. So if you tell a computer my name is Leo, it will not understand. If you tell a computer je m'appelle Leo, it will not understand. But when a compiler takes what the code that you have written and translates it into ones and zeros, the computer understands it. So that is just basically the idea behind compilers and interpreters and what they do, basically. So now next is input and output devices, also known as peripherals. So what do these devices do? As you can see, you have the joystick, the monitor, the internet modem, the scanners, the keyboard, the mouse, the printers, the handheld devices, just like your table phones. Those are the old phones, not these newer phones that don't use cable, sorry. and external CD drives, speakers. You know the idea. These are things that we use. Today, some of these components have been compressed into very tiny devices. In fact, some of them are actually compressed into a very small device now that we don't even notice their presence, in our machines. So basically, that's what peripherals are. Okay. So this is an in-depth lecture. So our in-depth lecture has started. So I'll advise some of us now to take a break, um, go and cool yourself a little bit and come back, because this is going to be long. But this getting a good understanding of this section will really help you in the future if you want to be very good at programming, or if you want to study computer engineering in school. Now we'll go in depth into what goes on in the computer, and I'll try to go through this as quick as possible because we have spent so much time. So basically, when you work with a computer, what you're doing is, sorry, what you're doing is you're giving the computer data. The computer processes your data and displays the information at the output, which could be your screen, which could be your printer, anything. It just displays the information on the results after processing it. A computer can be broken into, I'll break it into four sections. First is the central processing unit, and then you have the memory and the input and the output. So when you send information to the memory, the CPU basically takes information from the memory, processes it, sends it back to the memory, and some of them are actually sent to the output, some of them are not. So not every information that you process needs to be displayed, but that's just the idea. You have the memory, you have the CPU, you have the input, you have the output. And then every instruction that a computer processes, or every data, is represented as bit stream of zeros and ones. As I said before, a computer basically works by manipulating ones and zeros, and yes, it's just a lot of zeros and ones that does everything that you do with a computer. Now let's look at what I'll call the abstraction levels, or will I say, let me look at, let's call it the program life cycle, but sometimes abstraction levels might be a better word to use to describe this. So first, when using a computer, you have a problem, and then that is abstraction level one. You develop a program or a code or an algorithm. No, you have a problem, that's first. Then you develop a method to solve this problem. It could be, okay, let's say you want to learn how to do 20 push-ups. At first, you need to find the position where that is right to do the push-up. You don't just like jump into doing a push-up without knowing the way to do it, so you don't hurt yourself, or you don't do it wrongly. So an algorithm is basically your step-by-step process of solving the problem that you have, and then you choose a programming language. So that's the next, this one. Programming language could be anyone, could be C, could be Java, could be HTML. Sometimes certain programming languages are better to solve certain problems, so you need to take that into consideration. And then you have a system, a runtime system, which could be a virtual machine or an operating system, depending on your case or your situation. And then below the operating system, you have another abstraction called the instruction set architecture. We'll discuss more about that. These are in-depth concepts, as I said, so you don't really need to bother about this if you won't be studying computer engineering. And then below that, you have the microarchitecture, and below the microarchitecture, you have another abstraction, the logic, the circuits, circuit by circuit, I mean analog circuits, like resistors and those, but logic circuits are kind of slightly different. Then below the circuit are the electrons, the charges, the electric power or current that runs the circuit. So these are all abstraction levels when dealing with computer programs. If you can master these levels good, They're very good to know, and understanding the definitions is great. So let's go to the next. Um, let's look at, first of all, you have a problem. As I said before, you have a problem, you need to solve it. You develop an algorithm. An algorithm is a step-by-step process used to solve a problem, and then you choose a programming language. It could be anyone. You could choose one based on the fact that, okay, this one is easy to learn, or I already know this one, or it's fast, or it can be used for many things. There are many reasons why people choose programming languages when they make their designs. So you could actually sometimes use different programming languages to do the same thing, but there are certain languages that are just cannot be replaced. They are just designed for one particular thing, and that's it. So now below the language, now we have discussed the problem, we have discussed the algorithm and the programming languages like C in our case. Then below that we have the operating system. We have discussed that before. We said it manages the execution of your code or computer program or we have written to solve our problem. So when we write our code and we click run on the integrated development environment, or we run it, if we're using a command line, the operating system manages what happens from there. We don't have to do anything. You don't have to open your PC and take anything off. It's the operating system that does everything from there. So it's kind of like the new man in charge. When you just click run, it starts working from there. And then below the operating system or the virtual machine, then you have the integrated, you have the instruction set architecture. Now you have to listen very carefully to this one because it's a bit tricky. So the instruction set architecture is basically the interface between a computer hardware and computer software. It's kind of like the contract that your computer promises to satisfy, or you can call it an abstract model of a computer. I'll use myself as an example of an ISA. So let's say I tell you now that I can run fast, I can eat a lot of food within the space of 2 seconds, I have the hardest sponge in the world. Those are all statements. These things are not real. They're just statements that I'm making. But when you actually know that I can do it is when you see me do it. So an ISA is, you can think of an instruction set architecture like that. It's kind of like a contract that your computer promises to meet. Let's say it could be 3.4 gigahertz fast, and all that stuff. It promises to meet those specifications, but you don't actually know, until you actually implement it. So an example of an implementation of an instruction set architecture is a CPU, or a central processing unit. Now, for those of us that are very familiar with computers, the processors are sometimes made by companies like Intel or AMD, but somehow you're able to run Windows, you're able to run Linux on this, and how is that possible? So basically, so long as they follow the rules of the ISA or the rules set by the instruction set architecture, so long as Intel and AMD follow those rules when they design their hardware, it should work fine. You could run your Windows software on their chips so long as they say it meets that ISA specification, like x86 ISA, for example. You get to understand this as we move further. Now let's use the MIPS instruction set architecture as an example. Now this example might be brain wrecking for those of us that are not into the computer engineering program, but I'll try to break it down as possible. So the MIPS architecture is mostly used in engineering today, to explain to students because it's kind of relatively old and it's well documented. So the MIPS is a 32-bit architecture, and it basically describes how the 32 bits are broken down. You have a set of bits, that specifies the opcode. Another set of bits specifies the address of the source information or the source, let me see, or the address, the source address. Another information specifies the target address. Then the last information could specify something else. So this is just an example of, I think this should be an I type. Yes, this is an I type instruction. So you have the names is broken into I type, J type, and R type instruction. So with this basically I stands for instruction type, J stands for jump or branch instructions, then R stands for register instructions. Give me a second. I need to do something. All right. Okay. So basically, um, these are instruction types or rules that are used to describe the MIMS instruction set architecture. You have the ARM architecture, which is different from the MIMS. So long as your CPU, let's say your Intel CPU or your AMD CPU, follows the rules designed by MIMS ISA, that is for I-type instruction, it follows these rules, this separation, like the first, the 31st bit to 26th bit represent the opcode, and the 25th bit to the 21st bit represent the source register for an instruction type, and and the same thing applies to the J type and the R type. Your system should work fine. You could run many softwares on it, so long as it meets the MIMS architecture. Most of our PCs today don't run on MIMS, but they probably run on ARM architecture. And I mean, I won't want to go too deep into that, but basically you get the idea. If you look at this, you see just ones and zeros. So basically, when you send information, those information from your operating system, when it gets to the ISA, it just messes with them. It basically works with the ones and zeros that comes from the operating systems. So those ones and zeros are divided and manipulated based on the ISA that your hardware works on, and then you see all the things that you see, the output, it sends you back the output and all that. So this is basically what goes on, and I mean, if you would like to see more lecture on this, just let me know, because this can be really tricky, but just get the idea. MIMS work with 32 bits. This is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29. That's 1 2 3. So it worked with 32 bits at a time. I would want to go deeper into that. I think we'll spend too much time here. And we have different types of instruction sets architectures. We have different categories. We have the complex instruction set, we have the reduced instruction set. So the complex instruction set, they're a bit more complicated, but what differentiates them, I think, from the reduced instruction set is that reduced instruction sets are designed to run at lesser time. It takes less computing cycles to run a reduced instruction set as compared to a complex instruction set. Let's say it takes 1 cycle to run a reduced instruction set. It could take 3 cycles to run a complex instruction set. So another difference between them is that the complex instruction set can run multiple instructions at a time. It's many instructions at once. But the reduced instruction set can't run that much. It just picks the ones that are needed and works with them. So the idea behind this reduced instruction set is just to make your computer run faster, as compared to the complex one that might be used in better computers, like let's say the supercomputer, that has a big processing unit as compared to most of the ones that we use in our laptops today. So just get the idea. The reduced instruction set is widely used because most people, you have it's used in the hardware for your phones, and the concept is used in designing the hardware for your phones and your PC. But the complex instruction set is probably used for more complex computers. And then we also have other less popular instruction set architectures like the WI, the EPIC, MISC, and the OISC. You can see their meanings here. I mean, you don't really need to know this because you hardly see them in engineering school, really. Now let's go below the instruction set, which I just tell you it's like a concept, or let's say something that your computer promises to satisfy. It's not the real thing. Below that we have the microarchitecture right here. Now the microarchitecture is the implementation of an ISA. It's not visible to you, but it's basically blocks of hardware that implements what the ISA says. Let's say if I run fast, if I run very fast, imagine the microarchitecture being my legs and my muscles. It's the one that does the actual work. I told you that I run fast, but my legs are the things that actually run fast. So that's how you should think about the microarchitecture. It's a specific implementation of the instruction set architecture that is not visible to the software. The software doesn't see it. The ISA defines the rules and everything, and the software just sends it follows those rules. The designers of the software follow those rules, and they're able to design things for the microarchitecture, which is the hardware. So let's see. Implementations. The microarchitecture is a specific implementation of the ISA, which is not visible to the software, and you can think of it as blocks of electronics that implement one particular ISA, like the processor. Example is a CPU or arithmetic logic, which performs arithmetic and logic operations. Arithmetic operations like math, logic like and or. You get the idea. Yeah. So the implementation, now get this clear, it's very, very important. The implementation of the micro architecture could be different depending on the technology that is being used at that point in time. So the technology that was used in 1960 is way different from that that's used now. If you look at the computers that were designed in 1960, they were so heavy as compared to the ones that we use now that are so light. Everything has been made very small. So you'll see more about that in the future slides. So this is one architecture, the Intel 2 architecture, the Intel Core 2 architecture. Now this implements computing operations, and then you see another one that also implements computing operations, but you see that it is different. It's not the same as this, but they could probably do the same thing. Maybe one might be faster than the other, but they could probably do the same thing, in the sense that so long as these micro architectures follow the instruction set architecture, that's the rules that have been put in place, they are fine, they will run fine. But if they don't follow those rules, the hardware will have a problem. So now, thank God we have really passed this, and let's go now below the micro architecture. It's the logic. The logic circuits are probably one of the most important parts. I mean, they are all important parts, but the logic circuit is also important because it does the operation, the addition, the subtractions, the divisions. I don't want to go deep into that, but logic circuit and or not, XOR gates, they are the ones that perform those operations. I won't go deep into that because that will just be that's another lecture on its own. So just take note of that. Logic circuits, blocks of logic circuits are used to build a microarchitecture. So that's why you have below it is a logic circuit. Then to make these logic circuits, below them you have analog circuits that are made of resistors, operational amplifiers, transistors, all that stuff. So analog circuit, they take real world signals, sound, air, movement, all that stuff. They take it and when you combine these analog circuits, you are able to basically design or create a logic interpretation. So that's why you have the analog circuits right below the logic, because the logic circuits are built using the analog circuit, but the analog circuits get your signals, which your signals you can think of signals like the data, the actual data. So when you type, when you click on H now on your keyboard, the analog circuits interpret that H, or they collect what you have written and send it. It sends it as a signal into the logic circuit, and you get the idea. It takes the direct signal, and but it doesn't do any math with it or nothing. It's a logic circuit that performs the math, not the analog circuit. The analog circuit just takes the signals, which usually comes in forms of electrons. And yeah, you could also yeah, that's just the basic idea of an analog circuit. And then I'll say finally, we can in general think of all CPUs, single chip microprocessors or multi chip implementations, that run programs by looking at these steps, or look at them as performing the following steps. First of all, they fetch the instruction or the command from your code, they take in the input, then they decode them, that is, they translate your code, then they execute those codes, and then they either save them to memory, or sometimes they save them and write back, depending on what the instruction is exactly. Mostly, in fact, every instruction that you write goes through all these five stages: instruction, fetch, instruction, decode, execute, and saving to memory and writing back. Every instruction that you um, have on your code does this. And remember that sometimes this instruction run for multiple computer cycles. I mean, these cycles could be in the billions. They could happen within the split of a second. You won't even notice it. It's clocking really, really fast, and it keeps running until your computer turns off. So that's basically the idea. That's how it's able to get things fast. Your computer clocks billions of times in a single second. It could clock about 4 billion times in a second, so it could process up to 4 billion operations. And that's why when you click things on your PCs, it happens so fast. It takes in it fetches the information, or reads it in, it decodes it or translates it, processes it, writes back. All these things happen really fast. And in conclusion, I'm sure that at this point, most of us, including myself, I'm not used to talking so much, but some of you might be overwhelmed, which is understandable. But this will be the most difficult part of learning programming, if you ask me. I just did this so that you guys can know what goes on within your computer. You don't just jump into coding, because coding can be easy when you understand this concept. But when you don't understand this concept, it could be like confusing. You could be asking, why am I doing this, why am I doing that? And then that's because you don't have a strong background. So having broken all this down, we'll write our first code in our next video. And for those of us that made it to the end, I'd like to congratulate you. This is part of how hard it is to learn programming. We sit down for hours writing these codes. Everything happens by sacrifice, doesn't come easy. So guys, we have said enough. I will see you in the next video. Bye.